Hello everybody. Today let us discuss the Bitonic sort algorithm. Bitonic sort algorithm, like quicksort and merge sort, is also based on the algorithm design technique divide and conquer. The given list of n elements is divided into two halves, wherein one half will be in ascending order, the other half will be in descending order, and these two sub-halves are merged. While merging, the elements are finally sorted in whatever order we want, whether we want in ascending order or we want in descending order. Basically, this Bitonic sort is based on what is called as a Bitonic sequence. Bitonic sequence is a sequence of elements in which if the list consists of n elements, then the elements will be in ascending order from the beginning till some index I, and from the index I onwards up to the index n, the elements will be in the descending order. So, say for example, we have a sequence of elements 3, 8, 12, 16, 11, 7, 4, 1. So this is a Bitonic sequence. This array starts at the index 1. It has 8 number of elements, so it ends at index 8. If we can see, the elements are in ascending order starting from index 1 to index 4, and from index 5 onwards up to index 8, the elements are in descending order. So this is a Bitonic sequence. So we first form a Bitonic sequence like this, and then we merge these two subarrays, and while merging we see to it that the final list of elements will be in the sorted order that we want, either ascending or descending order. For the sake of simplicity, we assume that the number of elements in the list are a proper multiple of 2, that is 1, 2, 4, 8, 16, 32. If it is not a proper power of 2, then it will be difficult for us to merge the elements. That when we take an example, we will understand. We will first understand Bitonic sort by taking an array of 8 elements. Okay, let us write the elements vertically. So let us assume we have a list of elements 8, 3, 4, 9, 6, 2, 1, 7. Okay, these are the 8 elements we have, let us assume. So we need to form a Bitonic sequence. That is, we want the first 4 elements in ascending order and the next 4 elements in descending order. They are not anyways as of now. While merging we will do it, because we apply a divide and conquer technique, and we keep on dividing the array into smaller parts until we can solve the bigger subproblem. And once these two subarrays are in ascending and descending order, finally we want to sort this entire list of 8 numbers in ascending order. Okay, now the list of these 4 numbers, they are not in ascending order. The set of these 4 numbers are not in descending order. We will further divide them into 2 parts, wherein we want the elements 8 and 3 to be in ascending order, 4 and 9 to be in descending order, and this entire list of 4 elements have to be in ascending order. Same way, we will divide it into 2 parts, 6 and 2 ascending, 1 and 7 descending, and the set of these 4 elements in descending order, and finally the entire set in ascending order. Okay, so now since these 2 elements are not in ascending, they are not in descending, we will further divide it. 8 in ascending, 3 descending, and these 2 elements in ascending, 4 in ascending, 9 in descending, and these 2 elements in descending order. Okay, so now how do we do this? So to do this, what we will do is, now if we can see, the subarrays consist of only one elements, and this subarray requires that the elements be in ascending order. One element is by itself in ascending order, this one element is in descending order. So all the subarrays with only one element by themselves are in order, whatever order is required. So now we will merge and try to form the bigger subarray into whatever order we require. So here we require the subarray of these 2 elements to be in ascending order. So what we do is, we will compare these 2 elements 8 and 3, and we see that they are out of order. 3 is a smaller element and which is present after 8. So therefore we swap and they will be in ascending order. Same way we will compare these 2 elements 4 and 9, and we want them in descending order. 9, which is a larger element, is present after 4, therefore we swap it and these two elements are now in descending order. Next, we will merge the subarrays of size 2 to form a subarray of size 4. And when we are merging, once again we see in what order we want those elements to be in. Those elements are to be in ascending order, and we see to it that those elements will be in ascending order. Okay. So now let us try to understand the Bitonic sort logic very clearly when we are merging the subarrays of size 2. How does Bitonic sort work is, it compares the corresponding elements of the two subarrays. That is, the first element of the subarray with the first element of the second subarray. The second element of the first subarray with the second element of the second subarray. Or the first element with the third element, second element with the fourth element in a subarray of size 4. Okay. So now we will see how it happens. 3 and 9 are compared, the first element of the first subarray with the first element of the second subarray. And we see that they are in order because we want this set of 4 elements to be in ascending order. So 3 is smaller than 9, so therefore 3 remains there, 9 remains in its position. Then we compare 8 and 4. When we compare 8 and 4, we see that they are not in order. 4 is smaller, 8 is larger. Therefore they are swapped. 4 comes here and 8 will be here. The Bitonic sort doesn't stop here. The subarrays of size 2 were merged. Further, we need to merge the subarrays of size 1 finally to get the elements in ascending order. So therefore, what we do is we compare the subarrays of size 1. Okay, this subarray of size 1 is compared with this subarray of size 1 within this subarray. Okay, and this subarray of size 1 is compared with this subarray of size 1 within this subarray. Okay, so therefore, when we compare 3 and 4, we find that they are in order. When we compare 8 and 9, we find that they are not in order. So therefore, 8 and 9 are swapped, and finally we have the subarray of 4 elements which are in ascending order. That is what we needed. We wanted the subarray of 4 elements to be in ascending order. Now we will see how we will get the subarray of these 4 elements in descending order. So now we have subarrays of size 2 each. We have to further divide it into subarray of size 1. So 6 in ascending, 2 in descending. These 2 elements in ascending, 1 in ascending, 7 in descending, and these 2 in descending, and finally these 4 in descending. Okay, so now since each subarray consists of only 1 element, they are sorted by themselves. Now we will merge. When we are merging, we want the subarray of size 2, the bigger subarray, to be in ascending order. So therefore, when we compare 6 and 2, we will see that they are out of order. Therefore, we swap 2 and 6. These 2 are in ascending order, and now when we compare these 2, we want them in descending order. They are out of order, so 7 and 1 are compared, and these 2 are in descending order. Okay, now these 2 subarrays of size 2 have to be merged, and we want the final list to be in descending order. So what we do, we compare the corresponding elements. The first element of the first subarray with the first element of the second subarray. So if you take the original array of size 8, actually we are comparing the 5th element with the 7th element. Okay, the first element of the first subarray in the second half is nothing but the 5th element, and the first element in the second subarray of the subarray starting from 5 to 8 is at 7. Okay, and when we compare, we want it in descending order. We see that they are out of order, therefore we will swap. 7 will come here, 2 will come here. Then we compare 6 and 1. They are in order, so we will just leave it as it is. Okay. Now that the subarrays of size 2 are merged, we need to merge the subarrays of size 1. That is, we need to compare these 2 elements and we need to compare these 2 elements. So when 7 and 6 are compared, we see that they are sorted. 2 and 1, they are sorted. So now we have the subarray of size 4 which is in descending order. So now this is in ascending order 3, 4, 8, 9. This is in descending order 7, 6, 2, 1. Okay. So this subarray we wanted in descending order. So now we have a Bitonic sequence. Okay. So now this subarray in ascending, this subarray in descending, and finally the entire subarray in ascending. Okay. So one question may arise. Now finally when we merge these elements in ascending order, where is the descending part? So to get the elements in sorted order using Bitonic sort, if we want the elements to be in ascending order, we assume that the descending part in the array is empty. Or if we want the elements to be in descending order, then we assume that the elements in the ascending subarray are empty. Okay, so that is the idea. So now what we have to do, just like we did, here also we have to compare the corresponding elements and we need to swap if they are out of order. And we need to start from the subarrays of size 4, then we need to do the same thing to the subarrays of size 2, Then we need to do the same thing for the subarrays of size 1. Okay, we can't stop. So when the subarrays were of size 1, we just compared once. When the subarrays were of size 2, we merge the subarrays of size 2 and then we merge the subarrays of size 1 also. So same way, here we start from 4, the corresponding elements are compared, they are merged. Then we take subarrays of size 2, 2 each, we merge. Then we take subarrays of size 1, 1 each and we merge. So you can see this way the number of comparisons will keep on increasing depending upon what is the size of the array. If we have an array of 16 elements, then we will have one subarray of 8 elements, 8 elements. Corresponding elements are compared and merged. Then subarray of 4, 4 in this, 4, 4 in this, merge. Then 2, 2, 2, 2, 2, 2, 2, 2, they are merged. Then 1 each. So that is how the Bitonic sort algorithm works. Okay. So now the first element of the first subarray with the first element of the second subarray, that is the first element is compared with the fifth element in the list of n elements, and we see that they are in order because we want the final list to be in ascending order. So therefore we write it as it is 3, 7. The next second element of the first subarray with the second element of the second subarray 4 and 6. Once again they are in order 4, 6. Third element of the first subarray with the third element of the second subarray, that is third element with the seventh element, they are out of order, therefore we swap 2, 8. Fourth element of the first subarray with the fourth element of the second subarray 9 and 1, they are out of order 1, 9. Okay, we are not yet done. We have merged the subarrays of size 4. We need to merge the subarrays of size 2. Okay, so for that, corresponding elements of these two subarrays, corresponding elements of these two subarrays. So the first element is compared with the third element, that is the first element of this subarray with the first element of this subarray, out of order 2, 3. Because we want in ascending order. Now there is no descending component at all. 1 and 4 is compared, out of order, swap. So now 7 and 8 corresponding elements in the subarrays, they are in order 7 and 8, 6 and 9, they are in order 6 and 9. Finally we need to compare the subarrays of size 1. Okay, subarrays of size 1 needs to be merged, only then we have the final sorted list. So 1 and 2, 2 and 1, 3 and 4, 7 and 6, 8 and 9 needs to be compared. When 2 and 1 are compared, they are out of order, so we swap, we get 1 and 2. 3 and 4 when we compare, they are in order, 3 and 4 we leave as it is. 7 and 6 when we compare, they are out of order, 6 and 7 we compare. 8 and 9 when we compare, we find they are in order, 8 and 9. And now we can see this entire list of 8 elements is in ascending order, and that is what we want. So the descending part is assumed to be empty. Okay, so this is how the Bitonic sort algorithm works. Same way we can merge the two subarrays to get the elements in the descending order. Only thing is, when we are comparing, we need to see that the first element is smaller than the next element, and then we are going to swap so that the largest element will come before. We will see how the Bitonic sort algorithm looks like. Okay, algorithm Bitonic sort. Okay, it takes an array of elements which are stored in array named as A. The elements start at some position called as start, because when we have 8 elements, they are divided into two subarrays. The first subarray index starts at 1, the second subarray index starts at 5. So, and further when they get divided, the first subarray starts at 1, second subarray starts at 3. In this, first subarray starts at 5, second subarray starts at 7. So therefore, we will identify it by some index called as start, and let us assume there are size number of elements. Okay, the size, whether we have a array of size 8 or 4 or 2 or 1 or whatever it is, that will be identified by size, and in what order we want to sort the elements, whether we want to sort it in ascending order or descending order. We have seen it keeps on getting divided into subarrays of size 2, and every time upper half will be in ascending, lower half will be in descending. So that will be identified by that variable order. Okay, if size is greater than 1, okay, only if the size is greater than 1 we have something to do, like ascending, descending. When the element subarrays are of size 1, we don't have anything to do because they are sorted by themselves, whether it is ascending or descending order. Okay, what we will do, we will first find half size of it, because we will be dividing the array into two halves of 1 to n by 2 and n by 2 to n. So therefore half size is equal to size by 2. Okay, then we are going to sort the upper half using the same logic in ascending order. Bitonic sort the elements of the array A, which starts from the index start and which is of size half size. Okay, not all the n elements, we are taking only half the number of elements. So if the number of elements is 8, half size will tell that you need to sort only 4 elements, the upper half of the elements in ascending order. Then the lower half, Bitonic sort in the array A, but now the index doesn't start at start, it starts at start plus half size. Okay, so if the start is 1, half size is 4, 1 plus 4 5, so therefore the array starts at start plus half size. What is its size? Its size is also half size. Okay, because it also has 4 elements, but this we want to sort in descending order. Okay, and then we have to merge, Bitonic merge the array A, which starts at index start, whose size is size. Okay, in what order we need to merge? We need to merge in the order in which they are passing. Therefore here we are not going to specify the ascending or descending order. If the merge is called by due to this one, then it has to be sorted in ascending order. If it is called due to this, then it has to be sorted in descending order. So that argument will be dependent on whatever function call that initiates this Bitonic merge. Okay, so this is one part of the algorithm. Then we have another algorithm to merge. Okay, algo Bitonic merge A start size order. Same for arguments. Once again here, if size is greater than 1, we are doing something. If size is less than 1, we are not doing anything. What are we doing? Half size, because when we are merging, we saw that to merge, to get a final sorted list of 8 elements, we take 4 elements and then 2 elements and then 1 elements. So every time we need to take half size. Therefore half size is equal to size by 2. Okay, then what are we doing? We are comparing the corresponding elements in the two subarrays. Okay, so to compare the corresponding elements in the two subarrays, we will start a for loop for I is equal to start 2 start plus half size. Okay, means if we start at 1, it will go up to 1, 2, 3, 4 half size. If we start at 5, start plus half size, 5 plus 4, that is 5, 6, 7, 8. Okay, so therefore we start a for loop which starts at start and goes up to start plus half size. Okay, what are we going to do in this? If the order is equal to ascending, if the order is equal to ascending and A of I is greater than A of I plus half size. Okay, because we are comparing the corresponding elements in the two subarrays. Okay, A of I is 1, then A of I plus half size, 1 plus 4 is 5. So the first element will be compared with the fifth element, second element is compared with 2 plus 4 6, third element with 7, fourth element with 8. Okay, if the order is ascending and the first element is greater than the fifth element, second element is greater than the sixth element, so on and so forth, we need to swap A of I and A of I plus half size. Okay, same way, else if order is equal to descending and A of I is less than A of I plus half size, okay, so in this case the order is descending and the first element is smaller than the next element, so therefore the next element is bigger, that has to come first. in that case also we are going to swap a of I and a of I plus half size. Okay, and if you can recall, the algorithm doesn't stop here. As soon as we compare the subarrays of size 4, we don't stop. Okay, we will continue further. What are we going to do? We are further going to divide the array into half sizes and then we are going to merge them. So therefore, how are we going to merge? Using the same logic. So therefore, we need to call the same function again recursively, Bitonic merge A, which starts at start of size, half size, in what order? In whatever order this algorithm calls it. Okay, then the other part, Bitonic merge array A, which starts at start plus half size. Okay, of size, half size, in order, whatever order. Okay, so these two calls will make sure that once we have merged the subarrays of size 4 each, the upper part of the subarray will be further divided and the recursively it will be called. The lower part of the subarray will recursively be divided and it will be called. Okay, so only after all these things happens, finally the elements get sorted in the ascending order, descending order, whatever we want, depending upon what we are passing. So now, where are we mentioning that we want to sort the elements in either ascending order or descending order? So that will be done when we give the first call to this Bitonic sort from maybe the main or from some other function. When we give the first call, say Bitonic sort, the elements are stored in some array A, and if the start is at index 1, let us assume, okay, the array elements start from index 1, 2, 3, 4 and so on and so forth. Okay, then size, number of elements, we have n number of elements, and here we have to tell ascending. So this initial call is the one which will tell finally in what order we want the list to be, whether we want the list to be in ascending order or descending order. So this is the final call, ascending. Okay, inside whatever we were telling ascending, that is this call, and internally when we were telling descending, that is this call. So here it is only dividing the array into subparts of ascending, descending, further ascending, descending, so on and so forth until the size becomes 1. When it becomes 1, it stops, because here we are telling the size has to be greater than 1. If the size becomes equal to 1, it stops and comes out. So finally, how it gets sorted in ascending or descending order is by this function call from outside, which we call with either parameter as ascending or descending. If it is ascending, the final list will be sorted in ascending. If it is descending, then the final list will be sorted in descending order. Okay, so this is the algorithm for Bitonic sort. Now let us quickly analyze the efficiency of Bitonic sort. So we will follow the same steps that we followed earlier. What is the input size? Input size is the number of elements in the list. Okay, number of elements in the list, that is n number of elements will be there in the list, so therefore that is the input size. Okay, what is the basic operation? So let the basic operation here be the key comparison operation, because we will be performing key comparison operations extensively to finally sort the elements. The key comparison operation, which key comparison operation? So this key comparison operation, a of I greater than a of I plus half size, a of I less than a of half size. Okay, so those two key comparison operations, a of I greater than a of I plus half size and a of I is less than a of I plus half size. Okay, these two comparison operations, key comparison operations, will be our basic operation. Okay, now next let us assume, let C of n represent the number of times the key comparison operation is performed. Okay, So now, does the algorithm have best case, worst case and average case? If we look at very closely, the algorithm doesn't have best case, worst case, average case, because whatever the order of elements, it will simply divide it, it will compare, and only after comparing it will conclude the elements are in the sorted order from the beginning. So therefore, the algorithm doesn't have any best, worst and average case. Okay, let us try to write a recurrence relation for this, because this is a recursive algorithm. So how many times the basic operation, that is the key comparison operation, will be performed to sort a list of n elements? C of n is equal to. Now if you see this Bitonic sort algorithm, it calls the same Bitonic sort twice and it calls Bitonic merge once. So in this Bitonic sort call, it will further repeatedly call it, and it will call merge also, but it will be repeatedly calling. We don't know how many times the basic operation is performed, that is key comparison is performed within this call, but we know that the size will be reduced to half. So therefore, the number of comparisons to sort a list of n elements is the number of comparisons that will be required to sort the upper half in ascending order, again the lower half, the upper half in descending order, C of n by 2, plus C of n, plus we are performing then we call this merge, and in this merge we are doing some comparison operations. This will result calls to this will result in calls to this. After this separately calls this, so therefore this we have to account for. So therefore C merge of n. So now we have the upper half of n by 2 elements, lower half of n by 2 elements, then finally we have to merge these two halves into a final array of n elements, and there we are performing some number of comparison operations. Okay, now we need to solve this, so we need to know how many comparisons are we doing in the merge. So now I already told you, see, if you have to merge subarrays of size 4 to get a final array of size 8, then the 4 elements in the first subarray are compared with the 4 elements in the second subarray. First with 5th, second with 6th, third with 7th, fourth with 8th. So if there are 8 elements to be merged, then n by 2, 4 number of comparisons are done. But we know that the algorithm doesn't stop there. The algorithm goes one more step, wherein it will be divided into subarrays of size 2, 2, 2, 2 each. And once again there the corresponding elements are compared. First with 3rd, second with 4th, 5th with 7th, 6th with 8th. How many comparisons totally? Once again 4 comparisons. Okay, here 1, 2, here 1, 2, 4 comparisons. But the algorithm goes one more step, one element each. First, second, third, fourth, 5th, 6th, 7th, 8th. How many comparisons? Once again 4 comparisons. So how many times was these 4 comparisons done? The 4 comparisons was done 3 times. Okay, so now how can we get a proper estimate of this? When we have an array of size 4, how many times we are doing these comparison operations to get a final sorted list of 4? Okay, so in this 4 we have two elements, 2 comparisons, that is once again n by 2 number of comparisons once, and another time a single element twice. So to get a proper idea, we take a larger size. Let us take elements of size 16. So 16 will have 2 subarrays of size 8 and 8. So we will compare the corresponding elements. How many comparisons? 8 comparisons. Okay, 8 comparisons, that is n by 2 number of comparisons once we do. Then in these 8 elements we are going to perform comparisons, okay, by dividing it into size 4, 4. Okay, then 4, 4 to 2, 2, then 1, 1. So from 8 we know how many times we do it. We do it 3 times. So if it is 16 we do 4 times. If it is 4 we do 2 times. If it is 1 we do 1 times. So now if we see very carefully, then we can notice that C merge of 1 is nothing but we are doing n by 2 number of comparisons log n number of times. Okay, log n number of times. Because if we have 16 elements, we are doing this n by 2 comparisons 4 times. Log 16 is 4. If there are 8 elements, then we are doing log 8 to base 2, that is 3 times. 4 log 4 to base 2, 2 times. 2 log 2 to base 2, 1 time. If we have 32 elements, then 32, 16, 16, 8, 8, 8, 8, 4, 4, 4, 4, 4, 2, 2, 2, 1, 1, 1. So therefore, the number of times this n by 2 comparisons will be done is 5 times. So every time it will increase by 1. So therefore, the C merge of n is equal to n by 2 into log n. So if we solve this recurrence, then we should get the order of growth of Bitonic sort, which we will do now. we have the recurrence C of n is equal to 2C of n by 2 plus n by 2 into log n. Base 2, we will eliminate this base 2, okay, for time being, for the sake of simplicity, okay. And now to solve such recurrence, it is always better for us to assume let n be 2 to the power of n, so that it will be easy for us to solve, okay. This implies that, 2 to the power of k, n is equal to 2 to the power of k. This implies that k is equal to log n to base 2, okay. Now we will substitute accordingly, therefore this expression becomes easier for us to solve. C of n is 2 to the power of k, 2 to the power of k is equal to 2 times C 2 to the power of k by 2 plus 2 to the power of k by 2 log n to base 2 is nothing but k, okay. So this is the expression we get. So now what we can do is 2 times C, this 2 can come because both the bases are same, 2 to the power of k minus 1 plus 2 to the power of k minus 1 into k, okay. So this is the expression we get, okay. Now we will try to solve this. So when we try to solve this, we have C of 2 to the power of k minus 1. To find C of 2 to the power of k, we need C of 2 to the power of k minus 1. So how do we know, how do we do this? We need to backtrack because we don't know what is the value of C of 2 to the power of k minus 1. We will write it aside, C of 2 to the power of k minus 1, and we will substitute in a similar expression and find out what we get, okay. There has to be a 2, the 2 we will write, C we will write, it is 2 to the power of k minus 1. When we have k here, it is k minus 1 over here. So therefore when it is k minus 1 over here, it has to be 2 to the power of k minus 2. Okay, it has to be 2 to the power of k minus 2 plus, there has to be 2 to the power of, when it is, whatever is here, it is same here also, or if it is k here, it will be 1 less than that. So therefore it is 2 to the power of k minus 1, that is k minus 2, 1 less than this, into k. Okay, so this entire thing has to be replaced for this. So when we replace that, we will get it as 2 into that entire thing, 2c 2 to the power of k minus 2 plus 2 to the power of k minus 2 into k. That is the whole thing for this. This term appears as it is 2 to the power of k minus 1 into k. So this is the term over here. This entire thing has come from there. Okay, it is for the sake of simplicity we have written there so that we don't get confused. Okay, so now we will remove these brackets. When we remove the brackets, we will get it as 2 into 2, 2 squared c 2 to the power of k minus 2 plus this 2 into this 2 to the power of k minus 2. So 1k gets added, so k minus 2 plus 1, so therefore it is 2 to the power of k minus 1 into k, okay, plus 2 to the power of k minus 1 into k. So we can see this term is same, okay. So therefore we will write it as 2 squared c 2 to the power of k minus 2 plus 2 times k into, I will write k first, okay, k into 2 to the power of k minus 1, okay. Now we can observe one thing. When the when we want for k, we have a 1 over here, we have a minus 1 over here, and k into 2 to the power of k minus 1 is multiplied 1 times. When we have 2 here, we have k minus 2 here, and k into 2 to the power of k minus 1 is multiplied 2 times, okay. So we will see whether the same pattern follows. 2 squared. Now for this c of 2 to the power of k minus 2, we have to find a similar expression. C of 2 to the power of k minus 2 is equal to 2 times c of 2 to the power of k minus 3, 1 less than this, plus 2 times 2 to the power of k minus 3 into k. So that when we substitute here, we get 2 times c into 2 to the power of k minus 3 plus k into 2 to the power of k minus 3, bracket closes. This entire thing comes as it is, 2 into 2 times k into 2 to the power of k minus 1. Okay, now let us try to solve this. So 2 squared into 2 is 2 cubed, c 2 to the power of k minus 3 plus, now 2 squared is there, so when we multiply these two, 2 to the power of k minus 3 plus 2, so therefore it will be once again 2 to the power of k minus 1, k into 2 to the power of k minus 1 plus 2 times k into 2 to the power of k minus 1. Okay, now this is k into 2 to the power of k minus 1, this is 2 times k into 2 to the power of k minus 1, so therefore this is nothing but 3 times k into 2 to the power of k minus 1. Okay, so now we can observe there is a pattern. When there is a 1 over here, k minus 1, and this is multiplied 1 times. When we have 2 over here, this is k minus 2 and this is multiplied 2 times. This term k into 2 to the power of k minus 1. When we have a 3 over here, it is k minus 3 and k into 2 to the power of k minus 1 is multiplied 3 times. Okay, so based on the same logic, what we can conclude is, if we proceed the same way up to some step I, then if we have 2 to the power of I, we should have C of 2 to the power of k minus I 3. So I k minus I plus I times k into 2 to the power of k minus 1. Okay, so I times will be multiplying k into 2 to the power of k minus 1. Okay, so now actually we want to eliminate this term. Only when we eliminate this term we will be able to get some expression. So how can we eliminate this expression? We forgot to write the initial condition in the beginning. C of n is equal to 2c of n by 2 plus C merge of n if n is greater than 1. If n is greater than 1, we are going to do all these things in the algorithm. Okay, if n is equal to 1, our basic operation is comparison operation. How many times are we performing the comparison operation? We are not performing any comparison operation, therefore the number of comparison operations is 0. That is, C of 1 is equal to 0. Okay, when n is equal to 1, that is C of n is equal to 0. C of 1 is equal to 0. So we need to make this term as 1. Okay, so how do we make that term as 1? So to make that term as 1, we need to have 2 to the power of k minus I to be equal to 1. Okay, so when will be 2 to the power of k minus 1 equal to 1? 2 to the power of k minus I, if it is equal to 2 to the power of 0. So the base are same. So therefore we want k minus I to be equal to 0, or we want k to be equal to I, or I to be equal to k. Okay, so now when I becomes k, this term will become 1, and if it becomes 1, it will be equal to 0. That is what we saw initial condition, C of 1 is equal to 0. If this term vanishes, then this will give us some expression that will be the order of growth. We will see what it will be. Okay, so now we want I is equal to k, so therefore that is equal to 2 to the power of k, C of 2 to the power of k minus k plus I is equal to k times k into 2 to the power of k minus 1. Okay, so this is equal to 2 to the power of k, C of k minus k is 0, 2 to the power of 0 is 1 plus k squared times 2 to the power of k minus 1. Okay, so now 2 to the power of k, C of 1 is 0, 2 to the power of k into 0 plus k squared times 2 to the power of k minus 1. Okay, this term 0 into something will get vanished, and we have only k squared into 2 to the power of k minus 1. Okay, now how will we get the final answer? So now we see here, what is k? K is nothing but log n. We can't have the final result in with respect to k because our input size is n, number of elements in the list, and number of elements is n, and we know that k is nothing but log n to base 2. So now when we substitute it, okay, so till here we have C of 2 to the power of k. So now when we substitute 2 to the power of k is equal to n, we have C of n is equal to k is equal to log n to base 2, log n to base 2 the whole squared 2 to the power of k minus 1 is nothing but 2 to the power of k by 2. Okay, that is equal to log squared n. You can write it as log n the whole squared, or you can write it as log squared n. Okay, 2 to the power of k is nothing but n. Okay, n by 2. Okay, log, we'll write it as log n the whole squared itself. Okay, so n by 2 into log n the whole square, we can eliminate the lower order term, and therefore the order of growth will be n into log n to base 2 the whole square. Okay, so this is the order of growth of Bitonic sort. Okay, we know that quick sort and merge sort in the worst case belong to n log n. Okay, this belongs to n log squared n or n log n the whole square. Okay, so therefore this is the efficiency of Bitonic sort, quick sort and merge sort, n log n. This is n log squared n. We can write it as n log squared n also.